All right, algebra students, we are talking about exponential functions, reviewing these main ideas that come from this whole chapter about everything that is exponential. Well, first of all, things that are exponential. Population is exponential. Anytime you are growing your money in interest, say you get 3% a year, whatever, lose 20% a year, all things have to do with percent. That has to do with exponential concepts. So, the next thing that you should really understand is that exponential really is telling you where x is. X is an exponent. That's why we call it exponential. An exponential is like a growing curve or a decaying curve. Okay? So we're going to talk about what makes things grow and what makes them decay, but you have to understand the formula. The formula is a times b to the x. For example, 2 times 3 to the x, or 1.2 times 0.25 to the x. Like, these are both examples of exponential growth. Now, the a value is what we call the y-intercept. This is your initial value or your starting value on the y-axis. And the b value is what we call the factor, and it can either be called a growth factor or it can be a decay factor, but it depends on b's value. For example, if you take 2 and multiply by 3, it goes up to 6. And if you multiply by 3 again, that makes it 18. So it's going to keep on growing, and that's because the b value is greater than 1. When the b value is greater than 1, for example, this 3 right here, that is what makes it grow. Now the y-intercept, when we were talking about the y-intercept a moment ago, that is your a value. 2 is where you start, and then you multiply by 3 and it grows. However, it doesn't have to grow. When you multiply by numbers less than 1, for example, in my example here, 1.2, if you start with 1.2 and you multiply by a quarter, it's going to go down. And if you multiply that by a quarter, it goes down. So as you multiply by values that are less than 1, you're going to see it decay or go down over time. Now, it doesn't go down forever. We have these invisible graphs, or these invisible lines near the graph's edge that we call an asymptote. And maybe it'd be better if I just graphed one in the calculator and we could study it. Let's do 2 to the x power. When you're talking about 2 to the x power, 2 times 2 is 4. Or times again, 8. And that's going to keep on growing as I plug in different values. But now, as I start going backward and think about, well, what do negative numbers give me? Negative numbers don't necessarily make it negative. In fact, it never makes it negative. It just makes it smaller. Instead of multiplying by 2, it's like you're dividing by 2 over and over. So as you plug in further and further negative values, this decimal for y just gets closer and closer to 0. So when we talk about domain, for exponential functions, the domain would be all real numbers. But when we talk about range, range is different. Range means it doesn't go up and down forever. It goes up forever, but only goes closer and closer to 0. You can never see any value for y that is negative for the function that I have. So for that, I may say, well, all the y values are greater than 0. They're all above that y-axis. So there's a quick review of those ideas. Here's some compound interest explanations. P we call the principal. Now, not like your pal principal, like your principal at school. Principal a lot of times really means like starting amount. Your starting money that you invest. R is the percentage rate. Now, we always take R and divide by 100 because you really want that percentage as a decimal. For example, if it said 25%, you need to divide that by 100 and R would be 0.25. N represents the number of times it's been compounded, number of compounds. And so it's real good to know kind of some basic words like quarterly, When you hear the word quarterly, I spelled quarterly wrong, let's pick that up. Quarterly suggests 4 times a year. Or you may see questions that use the phrase monthly. Well, monthly would be 12 times a year. Or maybe even daily. Daily would be 365 times a year. Sometimes students don't know that weekly, there would be 52 weeks in a year. And then the last one I hear is semi-annually. I see that one sometimes. If something is annual, it's once a year. Semi means it would be twice a year. And then T is just the time. And a lot of times it's in years or months or days, whatever the problem seems to be using for units. We're also going to use regression in this video. You do regressions because you need an equation, and you're going to give the calculator some type of list of values for the x's and the y's so that it can spit out some type of exponential equation in this form of a times b to the x. In fact, going back for just a moment, we'll talk about this formula here in a little bit, but this is really the same idea. This is a times some number. Once you calculate all that, that can be b, and then whatever nt's value, that's like your x. So that's why compound interest falls in this chapter, and that's why we're kind of talking about it now. So let's review some ideas that we just kind of talked about above. Identify the growth and decay factor and the initial value, or the y-intercept, in the following equations. So I'll do these two, and I want you to try number 1. For this one, you're looking at a times b to the x. So first of all, you want to be able to identify that the y-intercept is 4. And the b value, which is going to be growth in this case, the growth factor, it is 1.3. Now I picked growth because 1.3 is bigger than 1. If you start with 4 and multiply by 1.3, it'll go up slightly from 4 to 5 something. This one I wanted to do because it's a little trickier. There's an invisible 1 in front of that, and that's not 16 now. That's like 1 times 6 to the x. There's your a, there's your b, and there's your x power. So I want you to try to do the same thing, identifying the y-intercept, and then whether that's growth or decay. So given a table of values, identify the growth factor. So the first thing I want to look for is trying to divide these numbers, like 5 divided by 1 or 25 divided by 5. You really want to see that all of these would give you the same multiplier. And basically I'm multiplying all of these by 5. Now the initial value can be easy to find as long as you know that that's when when x is 0. When x is 0, the other number is the y-intercept. So it looks like the y-intercept is going to happen at 0, 1. So knowing all that information allows me to figure out what the equation would be. So similar to that other problem, like 1 is an invisible number. I'm multiplying by 5, and it has an x as the exponent. And that 1 can be there, it doesn't have to be there. It's an understood value. When it's not there, we know it to be 1. So let's do another one similar to that. The y-intercept looks like 0, 4. That's my initial value. So when I go to build my equation, I know it's going to be 4 out front. And then I want to start studying the behavior of these, thinking about division. 12 divided by 4 would be 3, just like 36 divides by 12 to also be 3. So that means my growth factor is 3. This is 4 times 3 to the x power. You try the one next to it. I think on your paper I may have had some points here that I may have lost when I took a picture of it. So let me throw these in here for just a quick moment, and then we'll talk about it. Okay, so if I'm trying to write an equation, you need to be able to locate the y-intercept, that's A, and you need to recognize the growth factor, which is B. So in this first one, I notice that it's hitting at 1, and that is my y-intercept. And then from 1 to 2, 2 to 4, 4 to 8, it seems like I'm multiplying by x over and over. And so this can be your answer. You don't have to have the 1. It's understood if you don't have it. You can try 8 on your own. I'm going to try one of these decay problems. It looks like my y-intercept would be this 10 value here at the very top. And then this one is decaying. And if you notice, 10 goes to 5, 5 goes to about 2.5. So the way that you do division is you write it with a fraction that represents what you would be dividing by. And then, of course, put your x as an exponent in the top corner. If something is linear, we are looking for it to have an adding effect, like this one. Adds 3, adds 3, adds 3. This one is very linear, especially since these all add 1 consistently. The next ones, I may say, well, this one added 3, then it added 9, then it added 15. I know it's not using multiplication because 0 times 3 is 0. So I can't start with 0 and use multiplication. So I'm feeling like this one is more neither. But I do feel like there's some exponential behavior going on here. This seems to be multiplying by 2. So if I wanted to build an equation for that, this is an exponential table. It looks like my starting value is 2. I'm multiplying by 2, and then put the x on the exponent. So I want you to tell me whether you think these are linear, exponential, or neither, and really just focus in on the largest x power, or wherever that x is. That can really tell you what you're looking for. So the last thing I want to talk about is the compound interest formula. So the future value is the principal, 1 plus or minus r divided by n, all to the nt. Now, if you are decreasing, you can subtract in the formula. If it is increasing, then you add in the formula. So the first thing I want to do is read and label what information I'm given. If you invest a principal of $14,500, that would be compounded monthly. There's your n. And again, we talked about there are 12 months in a year. This is my R value, but only after I divide by 100. So if I divide that by 100, that is 0.045. And then lastly, they give me the time. They want me to do 8 years. So I'm going to replace everything in the formula. 14,500. 1 plus my interest rate divided by the compounded of 12. And then my power is going to be NT, or 12 times 8. So let's go to the calculator and see what that would be. 14,500, parentheses 1 plus, because it's increasing, 0.045, our 4.5% as a decimal, divided by the compounded monthly 12 times, and then that's raised to the monthly 12 times 8 years. So it looks like that's going to be roughly 20,769. Couldn't remember the first thing. It's 20,000 if I remember correctly. 20,769. And then since it's money, I may stop and round to the nearest cent. So that'd be 29 cents. Okay. So just watching my time there. That's 20, by the way. Kind of hard to read. $20,000. Now, for these other ones, you may try to explore, like for example, 14. 14, you're going to be able to set up a lot of it. Oh, you're losing, so I need to do 1 minus 0.067 as a decimal. It doesn't say I'm compounded at all. In fact, it just says each year. So that means my n is 1. And then it's 1 times t, and I really don't know what that is. So if I simplify this a little bit, if you simplify, you're going to get this equation. And I'm trying to see when is that less than 1,000. So if I go into my calculator and graph the equation in simplest form, I can go to the table and just kind of scroll through and let the calculator plug in different numbers until I figure out that it's roughly, it's somewhere in here in the 28th, 29th year. Hopefully this video was helpful. Good luck, and we'll see you next time.